Welcome to the last Tractography lecture and the last lecture of the FSL course. My name is Michiel Cotard, and here we will discuss several of the limitations of tractography and how we need to be careful when interpreting our tractography output, particularly when trying to talk about the connectivity strength between different brain regions. So what is it really that we measure when we estimate the number of streamlines connecting two brain regions? Is this somehow equivalent to the number of axons, to the proportion of axons from a seed region that reach a target region? Does it have something to do with the integrity of the white matter, how effectively they are connected with each other, how much myelination there is, how much packing density there is? All of these are things we might want to know to estimate the connectivity strength between two brain regions. Unfortunately, none of these are what tractography gives us. What we are measuring is that the probability that the dominant path through the diffusion field goes from region A to region B. So it's a sort of reproducibility analysis of a normal deterministic tractography. And even, that normal deterministic tractography is mainly just trying to claim something about whether a connection exists or not about the strength of that connection. Now, often you will still see this number of streamlines referred to as a connection strength. And that's not completely without any basis. So typically, any white matter bundles which are stronger in that they have more axons or more myelin will have a stronger anisotropy, and so will be easier to detect and to measure reliably in diffusion MRI, which means that they will be more reproducible when doing tractography. So while the reproducibility does not measure connectivity strength correctly, there is probably some correlation in that the stronger connections are the more reproducible ones on average. But the reproducibility that we actually measure will be affected by many more things, such as the connection length. In general, longer connections will have smaller probabilities because more streamlines will just accidentally move off the tract, and there will be fewer streamlines that are able to follow the white matter tract fully for if it's longer, even if it has the same number of axons as a corresponding shorter white matter tract. Similarly, actually, how crossing fibers behave might influence how well we can reproduce a specific tract. The stronger the tracts a specific tract crosses, the less streamlines you will be able to actually reproduce. And finally, even technical details, such as on what resolution we try to measure this path probability map, will affect what our final image looks like. Now, this doesn't mean that we should completely give up on using our number of streamlines as a measure of connectivity, but it's important to realize that we cannot use the number of streamlines as a meaningful connectivity measure when comparing between different tracts, because they will have different lengths, they will cross with different other fiber bundles, and so they will just be too different based on these other things to really have the number of streamlines being meaningful comparison. However, if we compare the same tract between different subjects, then they will have roughly the same length, they will have roughly the same geometric complexity, and so in this case, any variability between subjects is more likely to be something related with connectivity strength of that bundle, although it could also be related to the connectivity strength of some crossing fiber bundle or something else. So this is an important limitation to keep in mind when interpreting the path probability. In addition to that, there's complexity in that in just the limited due to the limited spatial resolution that we have in diffusion MRI. So this is, for example, shown in this figure in the lower left, where we have a lot of different fiber configurations, which, when we estimate the fiber orientations, all look very similar. A slight fanning configuration or just parallel fibers. We are in the end only estimating the mean fiber orientations in our balance stick analysis, so those two cases actually look kind of identical to us. And similarly, we can't really tell the difference between fibers which are crossing each other or fibers which are kissing each other or which are bending each other. In all cases, we will estimate two fiber orientations, and our tractography will kind of assume that we have the crossing fiber configuration and just pass straight through these voxel, even though we might have a bending or kissing configuration. So there's just a lot of ambiguity, and unfortunately in the diffusion MRI data there's not really the information to tell all of these different scenarios apart. So this is just an intrinsic limitation of using diffusion MRI for tractography. So this is just to illustrate this point a bit further, that we really have such complicated fiber configuration. So for example, in earlier talks I used the corpus callosum as an example of a region where we just have one fiber bundle running left to right connecting the two hemispheres. But if you actually look in electron microscopy, you have axons going indeed from left to right, but with a whole range of orientations. They all mix with each other. There's a lot of dispersion. And that type of behavior cannot just not be captured on the core scale that we have with our diffusion MRI data. And on the right is another example in the internal capsule, where we have seemingly some bundles within the internal capsule crossing each other, even though we estimate or typically only a single fiber orientation using diffusion MRI. And this limitation does lead actually to biases in our estimated connectivity. So here on the example, on the top here is an example where we have three regions of interest, and the top panel shows kind of the ground truth connection, where the upper left region of interest is connected with the other two through some voxel. But when we actually run tractography, what we will get in this voxel is that we will see two different fiber orientations. So we think there's crossing fibers. And so what we'll estimate is that it's actually the right ROI which is connected with the two others, because we can't resolve the actual sharp turns that the axons make in this case. And just to be clear, axons have, if you look under the electron microscope, axons do sometimes make very sharp turns of 90 degrees that tractography will just typically miss. Another example of these sharp turns that tractography will miss happens close to the gyri, where on the left we see the top left we see the ground truth configuration, where we basically expect fibers to run up to the gyri and then perhaps to have sharp bends into the gyral walls, connecting with the whole cortex. But based on the tractography, we can't really tell that scenario apart from the scenario on the right, where we just have the walls of the gyri connected with each other and just fibers coming up to the crown. So again, these two are somewhat equivalent, and based on the diffusion MRI data, we can't tell them apart. So we'll just get arbitrarily one of these configurations, depending on what tractography algorithm we are exactly using. A very nice example of the false positive connections that you can get between gray matter regions due to these ambiguities that we saw earlier was done in this study by Klaus Meisenhan, where they basically generated a fake diffusion MRI dataset, which was very much brain-like in that it consisted of 25 white matter tracts which were extracted from real data, but the simulated data only contained these 25 tracts. So we were sure that any other tracts which tractography found was a false positive in that there was not actually a connection between two regions, even though Tractography found it. And then they gave this simulated diffusion data to a lot of different groups around the world, running their tractography algorithms. And the general good news is that most of those tractography algorithms were able to reconstruct all or nearly all of the actual white matter tracts that were put in. But the bad news was that the vast majority of tracts they actually reconstructed, more than twice as many as the true tracts, are false tracts, which were new fiber bundles which were actually not in this data set. So this illustrates that when we estimate connectivity between two brain regions using diffusion MRI tractography, we should not take this as there actually being a connection, but rather just as an indication that there might be a connection. But to really confirm the existence of a new tract, you need some type of validation using post-mortem tracers or dissections to actually visualize this tract and to see that it actually exists. Now, after all this negativity about that tractography has these false positives, these connections that don't really exist, let's end up on a slightly more positive note, which is that tractography, when you actually try to reconstruct a known tract, is extremely accurate. So here we show the comparison between several cases where it's a chemical tracing has been used in post-mortem to visualize the tract, and that has been compared with the reconstructing that tract using tractography, and you can see an excellent overlap in all cases shown here, except that on the lower left we again see that in the cingulum bundle we had tractography suddenly turning off and doing its own thing. So this is again one of those examples of a false positives. But if we have decent regions of interest telling us where the tract starts, where it ends, then we can reliably reconstruct the shape of most of these tracts in agreement with what we would see in histology in post-mortem brains. And again, we saw this type of validation of tractography earlier when we looked at the postulation of the thalamus and the overlap between where we saw functional activity and where we saw the corresponding structural connectivity from tractography from that region to the cortex. So tractography is really a very powerful tool to estimate the connectivity between brain regions, but you have to keep in mind that there are real limitations in that a lot of the streamlines will not represent true underlying axons, but or even a real white matter tracts, but that but using correct ROIs, we can reconstruct known white matter tract, and we can use this info and we can use this to estimate the connectivity between brain regions, such as seen here, where we can reconstruct the connectivity between the prefrontal cortex and different parts of the brain through the acute fasciculus, and in agreement with the connectivity profiles that we would get from something like resting state functional MRI. And again, this agreement gives us confidence in both the connections that we get from tractography and from resting state fMRI. So, thank you all for paying attention.